ready to start? Is everybody back in? All right, I'm going to make this fairly quick because after Dave's talk, this is going to seem like duh 101. But we're going to go through it. How many people here were here for my my reverse engineering intro talk last time? So don't have to go through this too much. Here I am. I'm a noob. Always learning stuff. If you remember my last talk, I talked about this disclaimer that says when you're practicing reverse engineering on reverse me's and cracked me's that you find by Google, you need to be very cautious of those compiled binaries that you're testing on, and I advise you to do them in a secure environment and probably a sandboxed, isolated environment because you never know what might be inside of them. So that's sort of the basis of this talk. The talk is about code caving. Let's go back up to the top. Code caving, or why you should heed warning when downloading exes that you didn't code and compile yourself. So, wow, I just copied this from the other one. So what harm can be done by using an executable file that you find out on the internet, right? Well, Dave shows us about 7 dozen ways that set can harm you with executable files. But generally, we trust people to put these things up for our entertainment and our enjoyment, so we think, I'm just going to grab these files and I'm going to have at it. So what can you do with a compiled binary once you get it? You can study the structure with static analysis tools. You can open it in a debugger to try to see what it does. Sometimes it's easier to see what it does than other times, and we'll see that in a little bit. You can hex edit it, to play around with some static text strings in there, to change titles on things and have fun with it. But what else can you do with it? Obviously, you can Trojanize it, and people do. So one of the things that you can use a Trojanized executable for in pen tests is you can use it to carry a payload in a client-side attack. And SET obviously does quite a bit of that. So what we're talking about is code caving tonight, and code caving is essentially another name for inline coding. It's taking an executable, opening it up in some sort of format that allows you to actually edit the binary code itself and insert your own code in line. And you can do it by entering your own assembly. And there's some tools that you can use to do this as well. Again, we use some of the same tools that we showed in the earlier talk about reverse engineering. We're going to use OllyDbg tonight. So when you do this to an executable file, at a minimum, you're going to modify the hash signature of the file. So that's one way to tell if a file has been changed in its code from the original. It doesn't necessarily have to change the size of the file because, as we'll see, what we look for when we do code caving is slack space that exists in the code of the file already that we can use. So again, there are several methods of inserting malicious or fun changes into a binary file. You can use Metasploit tools to help you out. There are various virus generators, and I would advise against downloading those because you never know what's hiding in those for you as well. Or you can manually do it, which is what we're going to look at. So the manual methods, again, use similar tools that we looked at for reverse engineering. WordPE, I think Tyler showed that in his talk last time, OllyDbg, and a hex editor. And if we're going to put some sort of a payload in this, we would probably go to a source of shellcode like Metasploit framework and use MSF payload. So in the manual method, the first thing we do is we choose our binary. So in that binary, then we then find or create slack space. And again, slack space is space that's already allocated inside the file that doesn't have any code in it. And you'll see a couple bullets down, what that typically looks like are these strings here in your debugger. When you open it up into OllyDbg, you'll see like, it's 4 consecutive zeros or 2 zeros. And what I found is, and there's a caveat below here that I'll explain in a minute, when you see the strings of 4 consecutive zeros, what you're looking at is just virtual layout in memory based on the file structure, the PE header, and the section sizes as they're laid out in virtual memory, not necessarily the physical file itself. So it may show hundreds and hundreds of bytes of zeros in your debugger, but they don't really exist in the file yet. So one of the first things that people who start playing with this find out is when they'll start entering their assembly code in line, and then they go to save it to a file, and you get an error, and Ollie debug that says, we can't find this place in the file. It doesn't exist yet. So that's caveat number one. Even if the space isn't physically in the file, it'll still show up in the debugger. You have to ensure that the application isn't using that space for something. It may look empty now, but a good practice to use when you want to use a particular section of the code there that looks unused is to set some breakpoints on it, run the application, and see if you hit those breakpoints, if it's going to write to that particular section. And speaking of writing, the last caveat is that if you're going to stick a payload, for instance, that's encoded, that needs to decode itself in memory, that it needs to have, that section of code where you put it needs to have write permissions on that section. So, talking about the PE headers, the PE sections in a Windows executable. So when we go to find our slack space, if we can't find our slack space, then we have to create our own slack space inside the file. And to do that, we have to modify a section or add an entire new section to the executable file itself. And we would use a tool like Lord PE to do this, and I'll show you that in a minute when we get into the demo portion. Things you have to know are that when you change one of the properties of a section in an executable, it has a cascading effect on other sections, unless it's the very last section in the file, and we'll show that as well. And then finally, we have to create the actual physical slack space. After we change the header parameters, we have to create the space in the file, the null bytes, to fill that out so that when it's loaded in the debugger, you're actually saving to the real file. So, I'm going to run right into the demonstrations here. The first demonstration I'm going to show you, I just used the Windows calc.exe and did some fun stuff with it just as a practice. And calc.exe, and you'll find this similarly with other Windows applications. They have, or Windows native applications. They tend to have a lot of extra slack space that's really in the file, so you didn't have to do anything to the section header in this case. The second one, I'm going to show you that same reverse me executable that we showed in the last demonstration last month, where I did have to modify the section header. So let's move into okay, so the first one we're going to show you is calc.exe, and just going to start. Can everybody see that? Probably could be a little bit bigger, but I'm highlighting the native calc.exe without any modifications. And if I right-click it and I go to the properties of it, you'll see that the size is 114,688 bytes on disk. I go to my modified version of this, look at the properties, it's exactly the same size. So if you're just looking at file size to detect something that's out of the ordinary, that's not necessarily going to tell you anything. If I run a hash on those two files, it's going to come up with a very different value. So, what I did for this particular file, well, let's show you the file first, because this was just a fun one. So it's the calculator file, and it does everything that a typical calculator file should do. It's fully functional. The only thing I changed in it was a particular magic number that has something to do with the explanation of life, the universe, and everything. 42, right? So what I did was I found out where in the code, by playing with it in Ollie debug, that it would give me access to the value that's displaying in the dialog box. And I just did this through trial and error. I looked at some API calls, looked at the ones that I thought would be most likely to be looking at that value in that window. The get dialog item, set dialog item are very good candidates for that. And so when you put 42 and 42 shows up in that window, you get a message box that pops up. And the same thing, so if I did plus 42, again, equals 84. So you see anytime that 42 ends up in that dialog box, this code and my code cave is hit. So I'm going to show you that in the debugger now. Here are my notes. So I'm going to be looking for this particular subroutine, 1002604. sure you can't see that. You guys see that at all? I'm going to try to increase that font. All right, I'll make it real big. All right, so now we're at our original entry point, 1002. Is it 2604? 2604. Okay. All right, so right here is where we change the code. A breakpoint there. And if I go down here, let's go ahead. Here's my jump. See that jump? If I follow that red line all the way to the bottom of the code, I'm just going to quickly move down. This is a very long jump. You'll see a bunch of these. There's those DB00 calls at the bottom. That's the slack space right at the very bottom of the text section. This is just the text section, or the code section of the file. And here's my code in here. So it jumps to here, and what I did was I said, okay, at that point in the jump, what do my registers look like? What information can I gather from what's in the registers without having to create pointers and write stuff to various places and loop through? And I found out that 2 of the registers held information I was looking for. The string length in the dialog box itself, I think it's 2, it's actually 4 because it's actually 42-point space is how it comes out in this in the code. So we were looking for a length of 4, and we were also looking for the handle of the calc window, which was also in a different register. So I had all the information I needed to run my message box call. I went out and looked up the API call for message box. Now, one thing to note here is that this application already had an import for the message box API call. And it happened to be the message box wide, the Unicode version of it. So I had to pass my parameters into it as Unicode strings. So you'll see right here, Deep Thought was the title on the message box, and Life, the Universe, and Everything was the text message in the message box. And there are 00s between each of the ASCII codes for those letters. So essentially, that's what's calling the message box function every time it matches that 42. So if you want more information about that, I'm happy to step through it individually, but we don't have to go through the code and see what all the checks are. So calc.exe, we did not have to make any modifications. So now I'm going to open the reverse view. So this is the one that we looked at last month, right? So if I run this, this is one that says wrong serial number, right? And we look at them on disk. There's the original, and here's one I'm going to show you where I put an actual shellcode into it. Slight difference in size. That's because I had to actually create padding space for me to throw my shellcode into. And I guess I'll step through that real quick just to show you how to do that. So let me minimize these. So again, we're going to go back to that tool, Lord PE, which allows you to make modifications to PE headers and files. So I'm going to edit the original reverse me. And we come in here and we see some information that's useful to us. We know where the base address in memory will be. It'll be at 400,000 hex. We know where the entry point is going to be at 1,000 plus that 400,000. And then we will also see what our section sizes are in here. I'm going to go right into the sections and edit them. So what I'm going to do is I'm going to change the text section where the code is and make a few changes to it. I'm going to change the raw size on disk from 400 hex to 800 hex. I'm going to give myself an additional 400 bytes to play with, 400 hex bytes to play with. And when I do that, I then have to modify some of the other parameters because of that new 400 offset. So the virtual size of that particular section is going to change from 3F4 to 7F4 because I'm adding 400. And then all of these offsets below here are going to change by 400. The original offset won't because it still starts at the same place. The one that I'm changing still starts at the same place. So I right-click and say Edit Section Header. And I've got to close it first because it won't let me save it once I do that. So I'm going to change the raw size from 400 to 800 hex. And I'm going to change the virtual size from 3F4 to 7F4. And it still thinks it's open because I had it open. So let's try that again. Sections, edit. So again, size, changing it to 800. Changing this to 7F4. Okay, and now that we've done that, we need to change the offsets, the raw offsets to the following sections. We need to add 400 to each of those. So this becomes 1200 X. And again, their sizes don't change. We're not doing anything else to modify the other sections other than to move them down in their offsets. You know what, instead of doing this, this is taking too much time. I'm just going to say OK. I'll open the other one that I've added already, and you can see what the sections look like there. So we've moved those offsets down. This remains the same. The size increased from 400 to 800, and the virtual size increased. Those are the only things we changed. So now we have a padded version, and I'm going to show you in a hex editor the difference between the two. So here was the original, and if I go down to the bottom of the size of the original size, so the offset on disk was 400 hex, and then the size was an additional 400. So the end of that section should end right here in the original, and the next section starts right here with this 0C. That's at 800 hex. That's the original file. The padded version, at 800, you see all of these zeros here. So I use this hex editor to just insert 400 hex bytes, null bytes, to pad out that space that I'm going to eventually use inside the debugger. So I have that file that I'm going to open in Ollie. So we open the padded. It doesn't exist. So here's the raw file, and if I come down to the bottom, you should see those DBs. Again, that doesn't tell us much. I just wanted to show to you how it looks in the debugger. It's still functional in this case. I haven't done anything to it yet. So now I'm going to open another one that I've actually made some changes to. But before I do that, I'm going to shoot over here and show you just going to start a quick listener, and you can probably guess what's in the one that I'm going to open. So it's still functional. So if I'm playing around with this on my box, I think that I'm just playing around with the reverse me challenge, you know, getting wrong serial numbers here. But if I go back to my waiting.
You just didn't want to show Dave up. Oh,
there we go. Got our shell. It took a little bit, but we got our shell. So if I do DIR of that, I can see that I'm actually on that Windows box with my shell. And again, that other file is still functional. It's still running. And strangely enough, okay, it exited out there because I hit the exit code, but if I go back, I believe this is a process, so it should have spawned its own process. And I still have my shell on here. And I do. So I could exit out of this. I can do a PS. Sorry, not PS. What's the process listener? We're doing netstat. Do a netstat and see what we're listening here. So you can see we're connected on 443 back to that other machine. And I can see what the process number is over here. It's 2316. So when I go back over to the other machine and I start task manager 2316. Show processes from all user. There it is right there. So it's still running, even though it thinks that it is quick in memory. And some of you are saying, wait, it's an Ollie debug, right? So if I close that out, yeah, you'd be right. So again, I used a very simple shell here. One of the things you'll find that if you try to use some of the MSF payload binaries that you create, Some of the newer ones in Backtrack 5 and the latest versions of Metasploit tend to give debuggers problems, and I think that's because some of the payload writers have tried to put some anti-debugging code into them. So it's hard to do some of the things you need to do to fix up the file. So what I did was I used one from an older version. I happen to have a Backtrack 4 instance, and I used the very old Framework 2 MSF payload and did the Win32 reverse, which seems to work perfectly with any Windows executable I've ever used. And you can encode this or write your own encoder as well, and it should work just fine. The one thing you got to do to this file, however, is let's see if I have that code still in here. I do. All right. You'll see I'm piping the output of MSF payload here, sending it through a hex dump, XXD, and then I'm doing a replacement with sed here, and I'm replacing a string of bytes, 6AFFFF37 with 6A00FF37. This is a known bug, a well-known bug in this particular payload that causes your executable to hang indefinitely because you're passing a -1. That's the push -1 command as an argument to the wait for single object API call. And when you send -1 as a parameter to that, it waits forever, essentially. So I just changed that to 0 in the original shellcode that comes out. You do that before you would encode it, and then you can put it inside your executable. So back to here. Now let's take a look at that particular executable and what we had to do to it. So I'll look at this one a little bit more in detail. All right, so the very first thing that I did was I took the very first command here and I overrode it with a jump command to my code K. So if we follow this very top jump, I'm going to hit enter to follow it. I jump all the way to the bottom of the section. I'm now down into my code K where I created that slack space. I'm going to try to do some analysis on here and see if that cleans it up. Sometimes when you throw a payload, Ollie doesn't know what to do with it, and it doesn't know how to display the actual opcodes. So here's a couple of tricks you can do. You can try analyze code, and you can try, there we go. You can try to edit. You just select the garbage that you see. You do binary edit, and then just enter. Don't change anything, and Ollie usually fixes up the code for you. So the first two instructions that I insert here are push add and push FD. Push add takes the state of the registers and puts them onto the stack. And then push FD takes the state of the flags and puts them onto the stack. Now we preserve those so that when we come out of the bottom of our shell code, and it's done a lot of stuff with the stack and moved things around and changed flags, we want it back into the same state that it was in before we started this so that when we continue execution, it won't crash the program out. So we do that, and then this FC command was the very first byte of our shell code. So I could step through this showing you the shell code as it executes, but it's not really exciting. So I'm just going to go back down to the bottom here and show you what we do at the bottom. So here's the last 2 bytes of the shell code, the FFD0. Then we do a pop FD and pop add. So that's just pulling those flag values back off the stack and then pulling the register values back off the stack. And then what we have to do is, as I'm going through this, I do it incrementally. Create a breakpoint here. And I want to fix up the stack pointer at this point because the stack pointer is going to be several bytes off because of the operations that were in there. And that's the last thing we fix up. So I just determined that the difference between the stack pointer was hex A0, and so I do an add A0 to the stack pointer ESP to fix that up. So now it's in exactly the same state it was when I did that first jump from the top of the code. And then these 2 calls here are actually, let me see if I have the original. The first commands in the program were push 0, and the second command was that call jump to kernel 32 module, get module handle A. Those two commands got stomped when I put that jump in there. That's one thing you got to be aware of. When you start doing inline editing of assembly code in there, it's going to replace exactly the number of bytes that it needs for that opcode. And that opcode took too many bytes, and it basically knocked over the second two commands here. So you see that jump, you see these two knobs? So it overwrote those two commands, so you have to figure out whatever you've stomped on, and at the very bottom you have to recreate those commands. And so after we come out of our shellcode, fix the stack, I do my push 0, which is the very first command in the original entry point. I do my call to that, which is actually an address at the bottom here. You can see that at the bottom of the regular code. So that's right there. You can actually do call get module handle A, and Ollie will figure it out because it's been imported. It knows what the system address is, but I wanted to keep it as precise to the application itself, and what it was doing is doing a call to this pointer down here, 4013EE. So that's what I put in, and it automatically translated it to that jump kernel 32, the same thing you saw above. And then the last thing you do is you jump back to the next operation that would have executed had the code been intact. So I jump you can see that red line pointing all the way back up to the top of our code, down to that next intact operation. And that's what keeps the program operating while, meanwhile, I've got a shell on the other box. So that's essentially code caving. It can be used, to do fun stuff, like throw message boxes where they don't belong. I'm sure you could think of lots of other fun things to do. You're constrained by what API calls exist in the executable that you're working with. Obviously, it can be used to Trojanize things to use in pen tests. Some reverse me challenges actually require you to use code caving and create your own pointers to control loops and that sort of thing to avoid your registrations or your NAGMEs. That's it in a nutshell. Does anybody have any questions? That's a blank stage. Tyler.
So you pretty much went through this process manually. Are there any tools out there that allow you to kind of automatically do all this for you?
Yeah, as a matter of fact, Metasploit has the MSF payload that allows you to dump it right into an executable. You can dump it into a pre-existing executable template, so that you can take like Notepad or something and use that as the template and dump your payload directly into it. Automates the process for you. Probably wouldn't have run into all of the issues that I ran into with some of the newer payloads if I did it natively through Metasploit, but wouldn't learn a whole lot about how the files work. I did it that way. And as I mentioned early on, there are several virus creation tools. Do you know of any others that allow you to slipstream shellcode into other executable files? I definitely don't want to recommend any names for virus creation tools, because, as I said, they're built for nefarious purposes, and they often contain nasties in them when you download them.
I was just going to mention too that this isn't a new technique. This is one of the original techniques that file infectors used back in the 80s to infect viruses. So it's something that's been around for a long time.
Right, and this technique actually can gain you quite a bit in the field of antivirus evasion. If you get really good at this inline coding stuff and you can keep the program integrity intact, you can start writing your own encoder stubs. If you create your own encoder and you're going up against a signature-based AV, chances are you're going to be able to evade it, because the AV companies get all the stuff that Metasploit does. They get all the stuff even that Dave Kennedy's putting out there. Although some of his encoders are pretty advanced and polymorphic and using encryption, so it'd be hard to keep up with his stuff. But you can write your own encoders and use it on your pen tests.
So it helps not to be as famous.
Yeah, I would say so. Yeah, I mean, Metasploit, pretty much their payloads worked on everything 10 years ago, 8 years ago, and now, as soon as a new payload is released or a new module is released, AV companies are scrambling to build their signatures or their heuristics to detect it. And even most of the, when the encoding, MSF encode first came out, that was able to bypass, or most of those were able to bypass most antiviruses. And today, if you go to Virus Total, you'll see that most of those are detected. Even multiple iterations of the best ones, like Shikata Ganai, are detected by antivirus manufacturers. That's all I got. Give the shutdown slides. Give the ending slides.
Yeah.